we have block A as before, but now we're going to connect it to another block and then apply F on the second block. This is where Newton's third law is going to show up. Remember what we said last time? The first and the second law is always applied to a system. The third is always applied between systems. So every time you're going to see a problem with 2 subsystems, or 3, or 4, or 5, you know you're going to have to use Newton's third law to connect the free body diagram between systems. All right, they're giving us the mass of each. They're both on a horizontal frictionless surface. They're connected by a massless and unstretchable string. The force F is applied on B only, and they give us the magnitude. Oh, wow, nice. And they're going to see angle alpha. Cool. This causes both blocks to move towards the right. So we know the direction of motion, towards the right. The question is, we still don't know whether it's accelerated or not. So we still don't know whether we're going to use first law or second law. So let's keep reading. Oh, okay. Well, obviously, then we have an A. That's horizontal. Nice. Now, look at the first question. Calculate magnitude of the acceleration of A and B. Is that a stupid set of questions, or can the answer between 1 and 2 ever be different if they're connected by a string that doesn't stretch? Yeah, absolutely. Thank you, Tim. Perfect. So we know that the acceleration of one is going to be the same as the other. Same magnitude, same direction, horizontal towards the right. All right. Well, what are we going to do here? Well, we know we're looking for, what are we looking for? Oh, the acceleration, and then the tension between the two. So forces and acceleration. So we're going to use Newton. The question is, which system are we going to pick? The nice thing about Newton is it doesn't matter. Just pick one. If you don't know, just pick one. You should always be able to start. There is no way in this class that you should be stuck into a problem and not being able to start anywhere. Follow the method and pick something. So let's imagine don't know what I'm doing, so I have 2 systems, A and B, so I don't know. Let's pick one. Which one would you like to pick? System A? System B? Or heck, we can even pick system A and B. Brando suggests let's pick B. All right. So if you have 2 systems, make sure that you show me clearly which system you do. Let's start with B. All right, free body diagram on B. Obviously the weight, down. Be careful if you have more than one system. They will have different mass, therefore they will have different weights. So don't use W for all. Otherwise, as you combine the equation, no good. Don't use mg. Otherwise, as you throw them into the equation, no good either. So make sure that you write your mathematics clearly and carefully. Subscript are going to come back over and over and over. That's one subscript. We're going to add 2 later on, and sometimes 3. Those will make our life easy. If we decide to ignore them, guarantee is going to be wrong all the time. So physics is a good opportunity to take good habits and write our mathematics carefully. B is subjected by its own weight, no problem. It is in contact with the surface, therefore normal force. Let's call it NB because I'm dealing with B. Surface is horizontal, so up. Obviously there's a force acting on B given to us and defined by a vertical, which is along NB. And then obviously, imagine that you are object B, you're going to feel another force that's due to block A that is attached to you. So if you're being pulled towards the right by F, but you stay on the horizontal plane, you're going to feel something that tries to retain you behind you towards the left. That's the tension along the 2 blocks. Let's call it T. And I'm going to call it the tension from A acting on B, just to be precise. All right. Pick a coordinate system. A is going right, so I'm going to pick X right. Y up, don't matter. Let's apply back to chapter 2. Let's apply our vector knowledge, and let's write down the equation for this guy in both directions. Again, this must be a 30 seconds process. F sine alpha positive, F cosine alpha positive, X and Y direction. NB is 0 on the X, but it's entirely in the Y. TAB is negative in the X and is 0 on the Y. And MG is 0 on the X and negative on the Y. Now let's look at the physical constraint. Acceleration is the horizontal one, that's the one on X, therefore this is MEX and this is 0. And this M is the mass of B. Be careful about this. When you apply Newton's second law, the mass that shows up on the right-hand side is always the mass of the system you have identified. So write it on clearly, because this one will affect this one, and you can never go wrong. All right. 2 equations. How many unknown? I know F, I know alpha. I don't know NB. I don't know TAB. And I don't know A. So I'm screwed. 3 unknown, 2 equations. Don't even waste your time trying to do algebra. You ain't gonna go nowhere. You're gonna turn in a circle and pattern and vomit. The only fix is to get more equations. The only way, I'm sorry, I shouldn't do that. I shouldn't say that. One of the most common ways that we will be able to use this semester to obtain more equations is to analyze another system. So, if we just did B, let's do A. Free body diagram on A. The weight. We're doing object A, therefore the weight shows up for A. Be careful. Make sure you write that down. If you pick a coordinate system, or if you pick a system, the weight is always the weight of that system. There can only be one weight, the weight of the system you picked. If you pick A, the weight has to be the weight of A. That is, there should never, ever be the weight of B showing up in the free body diagram on A. And vice versa, there should never be the weight of A showing up on the free body diagram of B. That's a very, very common mistake if the blocks were on top of each other. So we're going to revisit this soon. So, weight first, normal force. Well, obviously, we have no idea whether the normal force acting on A is the same as the one acting on B. In this case, actually, it won't be the same. So let's never assume their magnitude. Give it different names. Therefore, different labels. Then, obviously, A is being pulled towards the right. F is not acting on A, because F, remember, is a contact force. It only applies on B. Doesn't apply on A. But there's a tension coming from B acting on A. And this tension tends to move A towards the right. When you're about to put the label is where you use Newton's third law. This is the tension B acting on A. Now look at the relationship between TAB and TBA. Obviously, this is what the third law is about. TAB is equal to negative TBA. Action and reaction. Magnitude is the same, the direction is opposite. So when you identify this, make sure you use the same label. Otherwise, you're going to have still too many unknown. That's where Newton's third law comes in. Since Newton's third law in this case only applied once, drop everything, and whatever T you use here is going to be the same here. Save your notation. So Newton's third law is the one that allows you to identify for sure that this guy is the same as this guy in magnitude. Therefore, keep the same label. If not, you're still going to be turning in a circle trying to reach and obtain more equations. That's it. So obviously B goes towards the right, A goes in the same direction with the same acceleration. So let's pick a coordinate system such that X is still towards the right, horizontal. As we write our two equations from Newton's second law, then obviously this is it. T is equal to ma in Ex. But this m must be the m of A. So be careful. ma times A. And in a y, we'll get 0. Okay? So now we have two more equations. So we have 4 equations. Let's see if we have introduced any new unknown. Nope. This one was here. No problem. This one was here. No problem. This is new. So now we have 4 equations and 4 unknown. T, NB, NA, and A. That's it. We have a system of 4 equations, 4 unknown. The rest is math. So just for the fun of it, we realize that NA is owned by itself on the 4th equation. Doesn't show up in any of the first 3, so obviously it's really only a 3 by 3. So let's solve for T, which is already done for us, and substitute in the first equation. And solve for A. Combining equation 1 and equation 3 gives us F sine alpha minus MAA is equal to MBA. Hence, the acceleration magnitude is F sine alpha divided by MA plus MB. Better be positive. Looks good. Meters per second squared. And they want, what do they want again? It was an annoying little, they want the tension. Oh, but now we have A, we can solve for T. Therefore, T is equal to MA divided by MA plus MB. That's a unitless number times F times sine alpha, which is also unitless. So this better be Newton. Easy. Good. Okay? So that's where the third law comes up. Every time you have more than one system, you're going to use the third law to relate common forces. And it's usually at the contact. So in your case, where the rope is located between A and B. Okay? You had another solution. Remember, you can pick any system that you want. We've picked B, we've picked A. Try to think outside of the box and give me another system that we could have considered. Anybody? This is an imaginary system. You can pick anything you want. It's a free country. And you will get the same answer. Yeah, thank you, Dyson. You could consider more than one system as your imaginary system. This will become fundamental in Chapter 9. The only way to do Chapter 9 collision and momentum is to do that trick. So make a note of it. It's going to come back very, very, very useful. And sometimes the only way to survive. Chapter 9. So let's imagine we pick A and B as one system. So this is our system. Between my red dashed line. As I'm going to do a free body diagram, I only look at external forces that are contact forces. So I'm only going to put a force if there is anywhere where my line is being intercepted. In this case, the intersection is F and N. Because again, the weight is a weird force, not has to be contact. So A and B. A and B, let's start with the weight. As I mentioned here, this must be the weight of this, that must be the weight of that, therefore, this must be the weight of both. All right. What else? Well, normal force. You can either have two, one for A, one for B, but since we consider A and B as one system, then really it's just one. N. this N is not the same as NA. So be careful. This is normal force for both system A and B. What else? Well, the force F. And then alpha was defined from the horizontal. Okay, so that's the free body diagram for system A and B. Let's use the same trick. This goes towards the right, accelerated. Therefore, I speak X positive here, Y positive there. And hence, my two equations are F sine alpha plus N is equal to MA plus MB A. And in the Y, F cosine alpha, plus N minus MA plus MB, G is equal to 0. Okay? Whether you use the first two from B, the next two from A, or you decided to skip object A and do object B and object AB, or skip object B and do system A and system AB, you will get the same answer. That's the beauty of picking your system. The only problem with this particular part 3 is choosing system A and B is nice for you to get A. Very easy, right? A from the first equation is F sine alpha divided by the total inertia, which obviously is the same, right? But this doesn't help you identifying the tension between A and B because it's not there. So that's the problem with A and B. But at least you get the acceleration. Okay? So the tension between A and B did not show up anywhere here because it's inside. It's inside your little red boundaries. And remember, Newton's law only uses and needs external forces acting on your system. So any internal force does not show up, which is why the tension between A and B do not show up on the last free body diagram. Okay?